Hey there, welcome to your very first day on the Caldi Acoustic Modeling team. I'm honestly super thrilled to be your mentor today. In this explainer, we're going to unpack one of the most elegant yet, initially confusing concepts in classical speech recognition, and that's two-pass decoding. Look, if you're going to be building or troubleshooting systems with Caldi, understanding exactly how and why we run inference twice is an absolute must. So grab a coffee, get comfortable, and let's decode this whole thing together.
Okay, here's a quick look at our roadmap for today. 1. The chicken and egg paradox. 2. The two-pass solution. 3. Decoding versus rescoring. And 4. Choosing your inference strategy.
All right, let's jump right into Section 1, the chicken and egg paradox. So, let's set the stage here. Imagine I hand you an audio file from a brand new speaker and I say, hey, run this through our best system. Sounds simple enough, right? Well, there's a huge catch. Our best model actually expects the audio features to be perfectly adapted to that specific speaker's unique voice characteristics before it even attempts to decode the words. So you might be wondering, how on earth do you decode an audio file when the model expects features you literally don't have yet?
To really understand the trap we're in, we need to quickly define two absolutely crucial terms. Our advanced models use SAT, which stands for Speaker Adapted Training. Because these models were trained on adapted features, they naturally expect adapted features at test time. The specific mathematical transformation we use to adapt those features to a speaker is called fMLLR. If you feed a SAT model raw, unadapted features, it's going to perform terribly. It absolutely needs that fMLLR transform.
And boom! This brilliantly illustrates our paradox. To estimate a new speaker's fMLLR transform, we need an alignment of their audio. Basically, we need to know roughly what they're saying to figure out how their specific voice maps to our phonetic states. But to get an alignment of their audio, we have to decode it. And to decode it with our SAT model, we need the adapted features. It's like you need an alignment to adapt the features, but you need adapted features to get the alignment. We are totally stuck in an infinite loop.
Which brings us perfectly to Section 2, the two-pass solution.
The fix for this loop is honestly pretty elegant. We just decode twice. Let's walk through the 4 exact steps. Step 1, or Pass 1. We decode the audio using an older, non-SAT model. Since it's speaker-independent, it doesn't need adapted features. This gives us a rough transcript and a lattice of hypotheses. Step 2, we use that rough lattice to estimate the speaker-specific fMLLR transform, which gives us our matrix A and vector B. Step 3, we apply that transform to every single audio frame. Our features are now mathematically shifted into a canonical, normalized space. And finally, Step 4, which is Pass 2. We redecode the audio completely from scratch, but this time using our powerful SAT model on the newly adapted features.
Let's anchor this to a concrete example so it's crystal clear. Let's say our test speaker, Sarah, says the phrase, "the cat sat." First, Sarah's raw audio passes through our non-SAT model. Now, it might make some mistakes. Maybe it thinks she said, "the bat sat," but it outputs a rough text lattice. We take that rough lattice and use it to estimate Sarah's unique fMLLR transform, which is essentially profiling her specific vocal tract. We apply that transform to our audio features. Now we're ready for Pass 2. We feed those adapted features into our highly accurate SAT Tri3B model, and out pops the perfect final transcript, the cat sat. Now there's a really crucial distinction regarding what we actually use from that first pass. Here's a massive pro tip from me to you. When we estimate the fMLLR in Step 2, we use the lattice, not just the single one best text output. A lattice provides a soft alignment over many different word hypotheses. Why do we do the extra work? Because if the first pass makes a recognition error, and it for sure will because it's a weaker model, a soft alignment is way more robust. It hedges its bets across multiple possibilities to calculate a much more accurate speaker transform. And since I want you hitting the ground running today, here's your cheat code. When you actually go into the terminal to run this procedure, you don't have to code these passes manually. You'll just use the built-in Caldi script steps/decode_fMLLR.sh. That script handles the entire two-pass dance automatically. Moving on, let's look at Section 3, Decoding versus Rescoring. Consider this your ultimate study guide. A lot of people confuse these two, so let's compare two-pass decoding for fMLLR directly against lattice rescoring. What's the action taken in the second pass? Well, in two-pass decoding, we redecode completely from scratch. In lattice rescoring, we're just updating the scores on an existing lattice. What actually changes? In two-pass decoding, the underlying acoustic features change because we applied fMLLR.
In Lattice Rescoring, just the scoring model changes, like maybe upgrading to a bigger language model. And most importantly, is the search redone? For two-pass decoding, yes, absolutely. For Lattice Rescoring, no way.
So, the crucial takeaway here is this golden rule. If the features changed, you must run a new search. That is two-pass decoding in a nutshell. But if only the scores changed, like for instance if you're just swapping out a small language model for a massive neural one, you keep the exact same lattice and just apply new weights. That's lattice rescoring. Burn this rule into your memory right now, and I promise you'll save yourself hours of frustrating debugging down the line.
Okay, nearly there. Section 4. Choosing your inference strategy.
So when do we actually use this? Well, not every model needs the two-pass treatment. Early-stage models like monophone, try-1, and try-2B models are strictly single-pass. And why is that? Because the transformations they use, like LDA or MLLT, are global transforms. They just don't require a per-speaker alignment to function. You only trigger the two-pass inference when you hit your complex try-3B models. That's because try-3B uses speaker-adapted training, which, as we know, inherently demands that per-speaker fMLR transform.
Now, I gotta share a really fascinating gotcha fact that bridges this classical architecture with modern tech. As you progress on the team, you'll start working with neural systems that use I-vectors, and you'll notice we completely skip two-pass decoding there. Why? Because I-vectors are a really clever shortcut. They feed speaker identity information directly into the neural network right alongside the audio features in a single pass, without needing to mathematically warp the acoustic features first. It completely circumvents that whole chicken and egg problem we talked about.
Which leaves us with a pretty provocative thought to end our session. We've just mastered this incredibly elegant, sophisticated two-pass fMLR dance. But as neural models and single-pass I-vectors become the absolute industry standard, is this intricate two-step destined to become just a legacy engineering relic? Or does understanding the deep logic behind speaker adaptation make you a much sharper architect for whatever comes next? I'll let you ponder that as you set up your workspace. Welcome to the team, and I'll catch you in the next explainer.